You're a newcomer to ham radio. You've just got your licence. You've managed to get yourself a transceiver of some sort. It's either second hand or you borrowed one, whatever. And you need an antenna, but you don't want to spend a lot of money. On the other hand, you want an antenna that works. Well, there is an antenna that works and is extremely cheap. It's called the Dipole. Hello and thank you for joining me on this video channel. This video is strictly for beginners, although those that have been ham radio operators for a little while may want to watch it and see if they can pick anything up. But it's about the dipole. The reason I'm talking about the dipole is because it's the simplest HF antenna really. It's probably the cheapest HF antenna really, and it's one of the most effective HF antennas, so it's got a lot going for it. When I first became licensed many years ago, one of the first antennas I put up was an 80-metre dipole. Now, I was very fortunate because I had a fairly large garden. I didn't realise how fortunate I was then, because it meant I've got to put a lot of wire out. And I think I must have gone down to the local ironmongers and got myself some twin flex, pulled it apart, because you get double the length for the price, and measured out the dipole. A dipole is a half-wave antenna. So on 80 metres, it means to say it's roughly 40 metres long, and mine was roughly 40 metres long, because in those days we didn't really have SWR meters. You could make one, I think, but I didn't have an SWR meter. All I had was a book that told me what the antenna length should be, and I believed it, and I suppose it was roughly right. I didn't have a balun. I had some I had some 70 ohm TV cable, 72 or 70 ohm TV cable, and I had a bell and lead connector on the end of it and plugged it into my home built transmitter, and it worked, and I quite enjoyed myself on 80 metres. I had no idea what the VSWR was because I didn't have a VSWR meter, and I really didn't know therefore whether it was resonant, but I knew it worked. And it did work, it worked quite well. So the point of all this is that the dipole is a very simple and perhaps forgiving antenna, although I have to say in those days when you ran valve transmitters, because there was separate transmitter and receiver in those days, when you had a valve transmitter you had a Pi network, and a Pi network was really like a built-in antenna matching unit really. So to some extent the fact that I didn't know what the VSWR was didn't really matter that much. I don't know, I never did find out what the VSWR was. Anyway, the fact is that a dipole is a very simple antenna, and I would say it's probably one of the best antennas to start with. The downside is that basically it's a single band antenna. Now, I don't suggest for one moment that you follow my example of just having a bit of random coax and a bit of wire. Let's be a bit more scientific about it. But I just give that as a demonstration to show you how easy it is, basically, to get a dipole to work, and to work very well. This is a bird's eye view of a dipole. In other words, we're up in the sky, we're looking down on the dipole. The total length of that dipole is a half wavelength, so if it was on 80 metres it would be 40 metres long, and if we had a 40 metre dipole, half of that is 20, so it would be 20 metres long. We have a gap in the middle, that's where we feed the antenna. Now let's first of all look at the radiation pattern, in other words the way that this antenna radiates. It doesn't radiate along that way, it radiates broadside to the antenna, so bear in mind we're looking down on the antenna. The radiation pattern of the antenna is something like this. It's bidirectional. I'd never make an artist, would I? Anyway, basically we're looking down on the antenna and it's radiating that way and that way. There is still some radiation from here, and in fact it's not quite as acute as that. There will be a bit of radiation from there and a bit of radiation from there, but not nearly as good as there. So your antenna is directional, but it's in two directions. And you will find that if the antenna is fairly low to the ground relative to the wavelength, in other words, let's say we've got a 40 metre dipole, so we've got a 20 metre length of wire. Provided that antenna is around about 7 or 8 metres above the ground, then it's not perfectly omnidirectional, but you get a fair bit of radiation from there, and you get reflection from, if you're in a sort of suburban area, you get reflection from houses, etc., etc. So basically, it's not a bad antenna, gives you general coverage, but it is biased broadside to the run of the antenna. Now let's get a clean sheet of paper. So we've got the dipole there. We're going to make this a 40 metre dipole, which means to say that the total length is 20 metres. Each leg will be 10 metres long. We'll come back to the precise measurements and how you adjust it later on. You feed the antenna with coax cable. Coax cable has got an inner conductor and an outer conductor. The outer conductor is usually a woven material. So we've got the coax cable there, and we've got the inner conductor there. The inner conductor goes to one side of the antenna, doesn't really matter which side it goes to, and the sheathing of the metal sheathing of the coax cable goes to the other side there. So you've got the coax cable there connected to the dipole. That's basically how you make the connection to your dipole. Let's first talk about how you calculate the length of the antenna. Ultimately, the length of the antenna will need to be adjusted slightly to take into account variations such as the wire you're using, the location of the antenna, etc., etc. But I'll put up on the screen now the two formulas. There's one formula which gives you the result in feet, and there's one formula that gives you the result in metres. Now, it's prudent to actually make the antenna slightly longer than the formula suggests, because that means to say that you can easily shorten it, but you can't make an antenna longer. Well, you can, but it's not so easy. So what about the wire for the antenna? Well, you can use any wire basically. You're looking for copper wire. Multi-stranded is good. A PVC covered multi-stranded is good because it weathers well. It doesn't really stretch. But any wire that conducts electricity will actually work as an antenna. Now, steer clear of electric fence wire and that sort of thing, but basically any copper wire will do the job. You might have some laying around, you might use speaker wire. It's not really critical. The main thing is that it's strong enough and it weathers okay. You must bear in mind there's a fair old weight, an antenna, the weight of itself is significant, so you're not going to get away with really thin wire because the coax cable that's connected to the centre will actually weigh on the antenna. But apart from that, it's not critical at all. So you please yourself. We do some nice PVC flexible covered wire, and I'll put it just on the video now, and that will do the job nicely. So how are we going to connect the two wires, because we've got a half-wave dipole which is cut in the centre? How are we going to connect that to the coax cable? Because you need a firm connection. That'll take a lot of strain in the weather. And believe me, I've had a few antennas that are broken because I've cobbled together something which really shouldn't have been cobbled together. Really and truly, the best way to connect the two wires together with the coax cable is to use a balun, a one-to-one balun. It's good practice to use that because it tends to make feeding the antenna a bit more docile. It preserves the radiation pattern and one or two other things, and it also makes a very solid connection between the wire and the coax cable. And again, I'll put one up on the screen here that we sell. It's not overly expensive, and I would thoroughly recommend you use that as a centre of your dipole. You'll need a PL259 plug at each end of the coax feeder. We do some solderless plugs now, which are quite good. If you're okay with a soldering iron, then fine, use a standard PL259 plug. But if you're a bit unsure, then we do some solderless ones, which again we stock, and that will make the installation easier. But make sure you make a good job of it, because it's one of the failures on antenna, or one of the failure areas on antennas is where the coax is connected, or rather where the plug is put onto the cable. If you don't make a decent job of it, then the weather will certainly show that it's not quite up to it. So make sure you put the plug on, and make sure you put something around it, wrap something around it, tape or something like that, just to make sure that it's waterproof. Now, earlier in this video I showed you the formula, so let's make an antenna that will work on the 20 meter band, the 40 megahertz band. So we take our formula and we work out the length of the half wave dipole. Now, I've chosen 14.2 megahertz, which is roughly centre of the band, and it comes out to a fraction under 33 feet. Well, we know that we're going to have to make some adjustments, so let's make it 33 feet. And we ought to add a little bit to that as well, because we want to make sure that if we have to make any adjustment, we don't run out of wire. So for 33 feet, I would say let's say 33 and a half feet. Sorry, it's in imperial, but that's the way I tend to work. But you can translate this, of course, into metric. You actually may want to increase that a little bit more to 33 foot 9 inches, and I'll show you why now. I bend the end of the wire back on itself so that we end up with a total length of 33 feet. Bear in mind, of course, that you've got 2 lengths of wire, so each length of wire will be 16 foot 6 inches. Anyway, I bend the wire back on itself. That enables me then to make some adjustments without cutting the wire. If I need to make it a bit longer, I just pull the loop out and I've got less wire bent back on itself, and if I want to make it shorter, I pull a bit more wire back into the loop. It makes it very easy, and you can do this very easily by just fastening provisionally with a bit of tape around it. I've used the tie wrap, but a bit of tape when you're making the adjustments would do fine. When you bend the wire back on itself, it actually has the effect of raising the frequency of the antenna, because it's shortening the antenna. It's not quite the same as cutting it off, but it has the effect of raising the frequency, which is akin to shortening the antenna, and we call that capacity loading. You should always use an insulator, because that gives you good isolation between the end of the wire and the support. If you were to put just some sort of nylon cord on it, when it gets damp, that would affect the resonance of the antenna. So always use an insulator at the end of, or each end of the dipole, as I've shown here. So we've now got our basic antenna. We've got the elements connected to a balun in the centre. We've got some coax cable going from the balun, which is long enough to go back to our transceiver. We've got the insulators on the end, and we've got the approximate right measurements of the antenna, but they probably won't be absolutely perfect. We need to make some adjustments, simply because the dipole is affected by height above the ground and by trees, etc., nearby. So we need to make some adjustments. Before we do any adjustments, there's one thing we need to add. Now, I would strongly recommend you add this, because it does make adjustment of the antenna much more logical and easy to do, and that is a line isolator at the point where the coax feed is about to be connected to the transceiver. The reason is because although the balun gives a measure of isolation, it doesn't solve the problem completely. You will still get an RF flowing down the outside of the coax, because radiation from the elements will actually be picked up by the shielding of the coax, and so you get RF flowing down the outside of the coax. And the problem with that is it can upset the VSWR measurements. So I always insert a line isolator at the point where the coax is connected to the transceiver. Now I'll just show a shot here of a typical line isolator. You just need a ferrite core and around about 10 turns of coax around the core should do the job. Now, if you're fortunate enough to have an antenna analyzer or VNA, then it does make adjustment very easy, because you can see on the graph where the resonant point of the antenna is. But although that's a great investment, and you may want to invest in one of those later on, because believe me, it's a really handy tool. It makes adjusting antennas so much quicker. But if you don't want to invest in one of those yet, you can use a VSWR meter, either an external one or the one built into your transceiver. Let me show you how you do it. This antenna, as you recall, is going to be for the 14 megahertz band, the 20 meter band, but the same principle applies if you wanted to use it for another band. You draw yourself a basic graph. That is 14.0. That is 14.175. That is 14.349. I say 349 because the band ends at 350. So you've got 3 frequency points. They're not super critical, but that's what I suggest. Then we've got 1-to-1 VSWR there. We've got 1.5-to-1 there, 2-to-1 there, 2.5-to-1 there. They're VSWR measurements. So what you do is you switch your transceiver so that it gives out a steady carrier. You can switch it to RTTY or switch it to AM. You only want a low amount of power, but you need to switch it to the SWR position on the meter. So with that selected, you press the PTT button briefly to get an SWR reading at 14 megahertz, and you make a point wherever that is on the scale. Let's for example say that it comes out at 1.5. Very lucky, you think. Great. Then you go to 4.175 and you think, oh, I'm not so lucky, because it's 2-to-1 there. And you go to 4.349, you think, oh gosh, it's got up right up there. Well, we join these together like that. What does that tell us? Well, it tells us that the resonant point of the antenna is either there or a bit further down the band. Quite clearly, basically the antenna is resonant a bit too low in the band, or even outside the band. So what we do is we shorten the antenna, because if the antenna is low in frequency, which it appears to be here, we shorten the antenna. If it was too high in frequency, in other words, the resonant point was there, we'd lengthen it. So we make an adjustment. In this case, we think, okay, it looks to me as if the antenna's too long, because it's either resonant there or it's resonant out the band. So we make an adjustment to the antenna by making it a bit shorter, and then we do another test. We think, oh, that's not so good, it's gone up. We do a measurement there, and oh great, it's gone down there. So 14.175, it's sort of 1.5, that's great. 14.349, we do another measurement, and it's going up again. But wait a minute, if I join these together, it gives me a nice curve. So it actually appears to be resonant there. And that's really how you do it. Provided you've accurately measured your dipole to start with, you should find that you've got a lowish VSWR point somewhere. Now, if for example, let's take the reverse now. I hope you can follow all these lines. Let's take the reverse. Perhaps the antenna is too short, which is why we put that extra loop on. So we do a measurement, and we get, wow, it's over 2-to-1 there. And we get another measurement at 4175, and it's basically about the same there. And we do another measurement at 14.349, and it goes down to about there. If we join those lines together, it shows the resonant point now is around about there, or maybe it's just outside the band. We need to move that resonant point in so that it's within the band. So in this case, because the antenna is too high in frequency, we need to make it a bit longer. So we pull the loop out again, and hopefully we'll end up with a curve like that. And that's how you adjust your antenna for resonance if all you've got is a VSWR meter. Now, finally, the position of the antenna and how you're going to install it in the garden. Ideally between two masts. You can't do that in a lot of cases, so the house at one end and a mast at the other end, or a tree at the other end, or whatever. It's not that critical really, and sometimes your garden is just not long enough. So let me finally show you a couple of ways that you may be able to fit the antenna into the garden without actually sacrificing the performance. Instead of having it horizontally, you can have it as an inverted V, like that. And that's where your balun is, that's where you feed it. The antenna will still work pretty well, and the good thing about the inverted V is you just need a single mast to support it, and the point of maximum radiation, which is always in the centre of a dipole, is where you need the height, and you'll have the height there. You need to make sure that these ends of the dipole are 2 or 3 feet above the ground, and also be mindful that they shouldn't be able to be touched by anybody that happens to be wandering around your garden, because they will be high voltage points when you're operating. Alternatively, what you can do is you take your dipole like that and just drop the ends like that. That enables you to get the dipole into a smaller space than otherwise would be possible, and again you get very good performance. The fact that the ends are dropped really makes no difference at all to the radiation pattern of the antenna, so that's another option. So there we are, that's how to make your first dipole. And you should have some good contacts. We're always told that the ideal height of the antenna should be a half wave above the ground. Well, that means to say that on the 20 metre band we've got to have it up at 10 metres or 30 odd feet above the ground. That's perfectly possible in a lot of locations, but not always. Don't get disheartened. Even if the antenna is only at around about 7 or 8 metres above the ground, you'll still get good contacts, and you'll work some DX. Believe me, I know, because I've done it. So I hope you found this video informative, and thank you for your support on this channel. I know it's very basic stuff at the moment, but there's a lot of guys around there that need this basic stuff because they've only just got a licence, or about to get their licence. And the great thing about a dipole is it is a surefire antenna. You will get some good DX. I've chosen 20 metres because, as the example, because 20 metres is a band that offers a lot of opportunity for DX, and DX can be working into Eastern Europe, or into America, or even into the Pacific, Australia, New Zealand, etc. It's all possible with a dipole. Just got to be on at the right time. And that's really all you can do. Get it in the position best for you in your particular garden. You'll have great fun. So thanks for your support on this channel. You take care, and as usual I'll look forward to seeing you in the next video. And by the way, if you want the bits and pieces for your antenna, don't forget that here at Waters and Stanton we carry them all in stock, and we offer a 24-hour shipping, so you know where to come.
Yeah, the bands are up and down this afternoon, unfortunately, but I'd have you, I would say about 5, 6, 5, 7 at the moment.